Homework questions, anything at this point, or do we want to wait until Friday after we've seen some more induction examples? Remember, we've got chapters 9 and 10 that are grouped together. Anything for homework questions? Anybody, anything? No, good, happy, excellent. Okay, so questions about the proof notebook, as long as I'm answering questions. Anything on proof notebook questions at this point in time? Alyssa, yeah.
So the one thing that I wasn't sure like how many to include would just be the definitions.
Okay. So now I need to pull up my rubric or document. Just one second, because I'm not totally sure what I said for the definitions. Give me just a sec, and I'm going to pull up my proof notebook assignment. Here we go. The list and description of the various mathematical symbols used in proofs over the course of the semester, that's what you're referring to?
Yeah.
Okay. As many as you need. So I would say for sure we've done the there exists and the for all, right? Those for sure should be in there. We've done the lives in, that's definitely one that should be in there. It depends on if you're using the such that or not. Sometimes that shows up, sometimes that doesn't. But I would basically just go back and look through your proofs and see what symbols we've used over the course of the semester and what you might want to include. That's my best suggestion at this point in time. There's no, like, I don't have an internal list that I'm working off of and checking off and say you have to have all of these. There's some, like the for all in it, there exists for sure. But other than that, I don't have a mental list of stuff I need to have included. Okay. Other questions about the proof notebook? Anything else at this point in time? Okay, we should be at the point where you have all of the different types of proof right now. So proof by induction is the last proof technique in there. So therefore, now or after today, whichever way you want to do it, you should be able to have all of the proofs included in your proof notebook. You might want to wait until you get back your homework that's graded on induction to make sure that everything's correct, but you should have all of the different types of proof that you need. Okay? Anything else? Other questions before we do some more induction proofs today? Anybody, anything? Good? Okay, today's goal is 3 induction proofs. That's what you're doing, 3, done, period. Once we're done with those, and I might put you in breakout rooms, we'll see. But 3 induction proofs, once we're done with those, we are done with class. So here we go. Let's do a whiteboard share. And let's start with summation 1. That's just a little more complicated than last time. Same basic idea, but a little more complicated. I won't bother to write down the steps that we had. It's the same idea as we did yesterday, right? We've got the base case, we've got the induction step. So those are my different steps in the proof, and I won't bother to write those down this time. Here's what we have. Prove that 3 to the first plus 3 squared plus 3 cubed plus a bunch of dots plus 3 to the n is equal to 3 to the n plus 1 minus 3 over 2 for all n living in the natural numbers. 3 to the first plus 3 squared plus 3 cubed plus a bunch of dots plus 3 to the n is equal to 3 to the n plus 1 minus 3 over 2 for all n living in the natural numbers. So again, it helps if you label your proof by induction. I am going to talk and write this one out, but I would encourage you, I wouldn't usually do this in class, but I'll do it right now. Half listen to me and half try to write it out on your own also. So do a little bit of, yeah, I hear Dr. Meyer's voice in the background, but I'm gonna try to write this stuff out while she's talking a little bit too, as opposed to copying it directly off the screen. Normally I encourage you to listen to me all the way, but this one's gonna be a half listen to me. All right, so we've got a base case, and that's gonna be n equals 1, we can come up with our base case equation. I need to show that 3 to the first is 3 to the 1 plus 1 minus 3 over 2. That's not clear enough to get labeled as a clearly, so we're going to need to start on one side of that equation and work to the other side. Usually it's easier to simplify than it is to expand, so we'll start on the right hand side. So we can say we know that 3 to the 1 plus 1 minus 3 over 2 is 3 squared minus 3 over 2. That's 9 minus 3 over 2, 6 over 2, which is 3, and that's 3 to the first. So that's good. We've got our base case. That's what we want to show. We can then go for our induction step. So we've got our induction hypothesis, what we want to assume. We can assume that 3 to the first plus 3 squared plus 3 cubed plus a bunch of dots, plus remember now we're changing to k, so plus 3 to the k is equal to 3 to the k plus 1 over 3 to the k plus 1 minus 3 over 2. And then I've also got my need to show with my k plus 1. So 3 to the first plus 3 squared plus 3 cubed plus a bunch of dots plus 3 to the k, we'll keep that one, plus 3 to the k plus 1 equals 3 to the k plus 1 minus 1 minus 3, sorry, 3 to the k plus 1 plus 1, you guys are half listening to me, people perked up with that one, minus 3 over 2. So 3 to the k plus 1 plus 1 minus 3 over 2. All right, with an arrow, and we know that, and we'll see if I can fit this all on one slide. My equations are going to be squished a little bit. We know that 3 to the first plus 3 squared plus 3 cubed plus a bunch of dots plus 3 to the k plus 3 to the k plus 1 equals, so I can do these first pieces by using my induction hypothesis. So we've got 3 to the k plus 1 minus 3 over 2. And then I still have that 3 to the k plus 1 piece hanging out at the end from the end of my equation. Common denominator would be good. So we can do 3 to the k plus 1 minus 3 plus 2 times 3 to the k plus 1 over 2. So we can do that. Can look and see what we're looking for in our need to show equation. My need to show equation has a minus 3 at the end in the numerator, and I've got a minus 3 in the numerator here, so that's good. We can keep that at the end. And then the other two pieces have a 3 to the k plus 1 in common. So let's try pulling that out, and hopefully we are going to get to where we want to be. So if I pull out a 3 to the k plus 1, in that first piece, there's nothing else left, which means I'm multiplying by 1. So I have a 1 left over. In the second piece, I was multiplying by 2. I've still got that minus 3, and then I'm still dividing by 2. This is the step where you got to kind of recognize the trick or figure out your algebra step. This is your algebra step at this point in time. So I can pull a 3 to the k plus 1 out. And again, remember, I have a minus 3 in the right-hand side of my need to show. So that kind of indicates that I want to keep the minus 3 in the numerator. Okay, 2 more steps, and then we'll be good. So we've got a 3 to the k plus 1 times 3. I'm going to write that as 3 to the first, just to make my next step even more obvious. 1 plus 2 is obviously equal to 3. We've got a minus 3, and then we've got over 2. And then when you are multiplying, you get to add exponents, which is great because this is going to let us end up where we want to be. So this is 3 to the k plus 1 minus 3 over 2. That's good. That's the right-hand side of our need to show. And so we can say our therefore statement. Again, I won't write it out, but we'll say therefore the statement is true as desired. So we won't write out the whole equation again. You can just say the statement is true as desired. All good there. Okay, give me a thumbs up, half listening to me, half doing this on your own. Yes, good, happy, all good? Okay. All right, the next thing that we want to do is an example of an induction proof that does not have a summation with it. So we're gonna see how induction can get used for a couple of different types of proofs. This next one isn't going to have a summation. For example, prove that 2 divides n squared plus n for all n living in the natural numbers. Prove that 2 divides n squared plus n for all n living in the natural numbers. Again, our for all n living in the natural numbers is our cue that we want to try an induction proof at this point in time. That's what we're looking for. So, proof by induction. I'm going to have you write out the base case, please. Go ahead and write out the base case. I'll write it here without talking. You can write out the base case yourself. Remember what our definition of divisibility is. How do I show that 2 divides something? I'm going to go back to definitions. We haven't worked with divisibility for a little while. We've been concentrating on sets. So go back to your definitions. Remember how divisibility works. Okay, so our base case is n equals 1, right? That means I need to show that 2 divides 1 squared plus 1, or remember my definition of divisibility, I need to show that 1 squared plus 1 is equal to 2 times sailboat for some sailboat living in Z. It ends up that your sailboat's just equal to 1. All good? Everybody's good there, so easy base case. Induction step. Writing out our assume and need to show. So we get to assume that 2 divides k squared plus k. Or I'm going to turn it into an equation right away. You could wait and turn it into an equation after you write the need to show. I'm going to turn it into an equation now. Either way is totally fine. So k squared plus k equals 2, I don't know, L. This is one where we know this equation is true. It's an assume, so we're going to give it a letter. For some L living in the integers, all right? And then I've got my need to show. So I need to show that 2 divides k plus 1 squared plus k plus 1. Got to replace that with your k plus 1. Need to show that 2 divides k plus 1 squared plus k plus 1. And again, we'll turn this into an equation. Or, this is a little messier, k plus 1 squared plus k plus 1 equals 2. I could use sailboat, but I use sailboat up above. It's not wrong if you use sailboat, but I'm gonna switch so that we don't assume that sailboat equals 1. So we'll go with 2 flower for some flower living in the integers. It's a good thing we're 4.5 weeks or 5.5 weeks into online learning and I can draw a flower with my tablet now. I think that would have been a disaster at the very beginning of this whole adventure. But there we go. There's my need to show. I've got a need to show equation. Normally I would ask you my very favorite question. You can answer my very favorite question in your head or out loud if you want, either way, but we are going to start on the left side of this equation. So here we go. We know that k plus 1 squared plus k plus 1. equals FOIL. Doing some FOIL would be good here. So we've got k squared plus 2k plus 1 plus k plus 1. FOIL is a definite good thing here. Looking back at your induction hypothesis, I can replace a k squared plus k. And I'm going to want to use my induction hypothesis somewhere. So if I have a k squared plus k, I can replace that with 2l, and then I need to keep the rest of my stuff. So here's my k squared, and then the plus k isn't next to it, but that's okay. We've got a k squared plus k in here. That's great. I can replace that with 2l. So we've got 2l. I have a 2k left over, and I have a plus 2 left over if I combine the two ones. We've got a 1 plus 1, and that gives me 2. Yay, you should be able to finish it from here. So keep writing, come up with your flower. I will write without talking, and then we'll finish this one and jump to our last example. All right, so your flower should be L plus K plus, let's try 1. I forgot to factor out the 2 from my constant. So let's try 1 here instead of 2, my bad. L plus K plus 1, and we've got an L plus K plus 1. That lives in the integers because K and L live in the integers, and we are using addition. Spectacular. Therefore, the statement is true as desired. Statement is true as desired. Cool. Okay, 2 things I want to point out, and then we'll talk for questions on this one. First of all, first thing, this statement, 2 divides n squared plus n, is something that you should be able to prove using a different proof technique. You don't have to use induction on this one. You can if you want to. And I wanted to pull an example where you're using induction on a non-summation, but you don't have to. Either give me a verbal answer or type it in the comments. What's another way that we could prove this one? What would you need if you wanted to prove this statement? Either raise your hand, volunteer, or you can type it in the comments if you want to. Either way, what do we got? How would we want to prove this one? Technique. I have proof by cases. Yes. Direct proof. Yes. Oh, you guys are still sending private messages. That works fine. You can do it to everybody if you want to. Yes, the general answer is a direct proof. Absolutely. And then the specific type of direct proof that you are going to need is a proof by cases. Cases with n being odd and n being even. So those two definitely flow together, and that's what you're looking for in this case. That's the first thing. So you don't have to use proof by induction for this one. You can if you want to. You don't have to. Second thing, we had a equation with k squared plus k, right? We were able to replace k squared plus k in our induction hypothesis, and it just so happened that we had a k squared plus k in the equation that we got. If we didn't have a k squared plus k, if we just had a k squared, then I could make one. So if I wanted to, I could make this into k squared plus k, and then I would have the rest of it plus 2k plus 1 plus k plus 1, and then I could subtract k off at the end. So it happened that we had exactly what we wanted, which is good. Sometimes you have to make what you want, and then you're just gonna have to add and subtract pieces. And we've seen adding and subtracting pieces before. Not super often, but we've seen that. So that's just something else to keep in mind. Sometimes it doesn't show up quite as nicely as it does here. All right, anything for questions on